Our third and final speaker for tonight is Associate Professor Alan Duffy from Swinburne University of Technology. Alan is an Associate Professor, as we said, of Astrophysics at Swinburne, where he creates baby universes inside supercomputers to unlock the physics behind forming galaxies like our Milky Way. Alan has a long-standing interest in public outreach. If not contemplating the wonders of the universe, you might find him on various ABC shows and radio programs, and also Channel 10's The Project. So without further ado, Alan Duffy.
Thank you very much. I've just realised the problem with the Pint of Science format. Well, it's fine for you guys. I have a microphone, a pint, but also a clicker, and I'm not sure how I'm going to make this work. So,
I'll drink you mine.
Alright, so I'll just take a quick sip. I'm going to wander over here so I can see my slides and get amongst it. If this goes squealy, horrible noise, just, let me know if my ears bleeding, and I'll walk away. So, I'm going to tell you about our search for extrasolar planets, basically exoplanets, and in particular a very special class, and those are called these Earth-like worlds, and the twins of our own world, our own Earth, that is the Earth 2.0. Not liking that. Was that you bumping into it? No? So it wasn't? Alright, I might have to wander away if that keeps happening. So in our search for Earth 2.0, it's really... Okay, I'm going to walk away from the microphone, from the speaker. I know. Alright. Was it popping? Alright. Really, when we're looking for Earth 2.0, what we're looking for is a habitable world, right? That's what we're interested in. We're wanting to find worlds that can potentially sustain life as we know it. And in particular, of course, that would be intelligent life, and I'll get to that. So where will we start looking for our Earth 2.0? Well, a good place to start is our own solar system, where we have Earth 1.0. So this is not to scale, this is my attempts at graphics, not quite as good as Mark, Mr. Zulu there. But here we have the planets of our solar system. When you're very far from the sun, it's very cold. The water is essentially frozen as ice. When you're very close to the sun, as in the case of Mercury and Venus, it's very hot, and that water boils off. And it's only at the region of the Earth, and maybe Mars, depending on its season, that it's actually warm enough to have liquid water. And that, so far as we're aware, is critical for life as we know it. That's one of the key ingredients for life. So when we're looking for our Earth 2.0, what we're really looking for is that special place from the star where liquid water can exist. Not too close, so it's not too hot. Not too far away, so it's not too cold. In other words, just right, the habitable zone, where you can get this liquid water, also known as the Goldilocks zone, which everyone knew, right? Pretty much? Alright, I'm telling you how it's okay, so that's fine. So, how do we go about finding, by the way, this is really easy to find planets in our own solar system. Except, there is a distant ninth planet we suspect, so when you're very, very far away from our sun, it is actually kind of challenging to find planets. So we're still searching. There's an online tool you can help us search for that. This is one of the citizen science projects. But that's not what I want to talk about tonight. I want to talk about finding worlds around other stars. So how do you go about finding them? Well, there's essentially three techniques. And through the course of these techniques, we're going to populate this graph. Now, I know that you're overwhelmed by the graphics of this. It's a graph, and it's actually also cut off as well, so it's even better, even more exciting. On the y-axis is the mass of the planets, or exoplanets, that we hope to find, and that's in terms of our Earth. So 1 is 1 Earth mass, 0.1 is the 10th of the mass, 100 is 100 times the mass of the Earth. And then we're going to find planets at a whole range of distances from their star. Again, 1 is the distance from the Earth to our Sun, 10 is 10 times further, and 0.1 is a tenth of that distance, roughly speaking, Mercury. So these are a sense of scale. So, as I mentioned, there's Mercury, It's about 0.25 AU, for distances from our sun. There's Earth sitting at 1,1 and Jupiter's in the top right. So, to populate this diagram, to find the alien worlds, how would you start? What's the easiest way to see a planet? To look? I hope someone said to look. This wasn't a trick question, this was like literally the easiest idea. You look, and there it is. There's a planet. Easy. This is an image from the Very Large Telescope. Australia just got access to this European Southern Observatory facility. It's 20 years basically in the making. It's been a dream of ours to gain access to these telescopes. And what we see is a red flamethrower. It's basically a disk of dust and gas seen edge on. Some of the material that Stefan was mentioning at the start that forms stars and indeed the planets from those that form around that star. The star itself is actually blindingly bright. It's blocked out. And the planet, glowing in reflected starlight, is that little guy. That's Beta Pictoris, P. So the star is Beta Pictoris, and the A is silent. And then the first object you find away from it is then B, second further C, and so forth. So, this alien world you can see with your telescope eye. The problem is, that star is blindingly bright. Effectively, it's like looking directly into the lights of the MCG and trying to see a firefly beside it, right? It's kind of challenging. So what we do is we block the MCG floodlights to try to allow us to see that little firefly twinkling in the dark. And that's what's been done. This blue disk is actually being put in front of the telescope to block that light. What that means is we really do need that planet to be very far from its star so that we don't cover it up with this technique. What that means is, going back to our exciting graph, those few worlds that we've seen directly are very big, so they reflect a lot of light, and they're very far from their star. So they live in this top right corner of the graph. Now, how else would you try to find a planet? Well, there's a technique called the radial transit. It's also called the wobble. As that planet goes around its star, so pulled by the gravity of the star, so too it pulls back on that star. Just not as significantly because the star is far more massive. So that star is wobbling around around their common center of mass. Now that distance is tiny. Even in our solar system, Jupiter is vast relative to all the other planets, but it can barely pull the sun around. In fact, the sun wobbles around a point still within its surface. So you would never directly see that. What you can, however, see is the change in the light from that star. This is called the Doppler technique. We've all heard it with ambulances, fire engines, whatever. As they travel towards us, the sound waves get compressed. So we get a high pitch, and then as it goes by, those sound waves get stretched out. It goes. I'm really pulling all the stops here for effects. Same thing is happening to the light. As the star comes towards us, in its wobble, the light is compressed. Shorter wavelength is bluer light, so the light from that star looks bluer. And then, as it goes around in its orbit, it is stretched. That's the ambulance going by you, dropping pitch, that is longer wavelengths, which is redder in colour. And that's what you're seeing pictorially represented at the bottom. This is an obscenely small signal. The Earth causes a change in velocity of a star at about the pace of a toddler crawling. I know some parents here might think that can be alarmingly fast, right? They go through the sockets or whatever, but that is still extraordinarily tiny signal to pick out from a very distant star. And yet, that's what we're doing. Routinely, we're seeing these kind of wobbles in these stars. So if we go back to our diagram, what we see is a whole swathe of new points. All of these are big objects. The bigger they are, the more they cause their star to wobble, the easier they are to see, so unsurprisingly that's what we're seeing first. So we find our diagram populated. So what we're seeing with this technique are essentially all worlds bigger than the Earth. In fact, they're about the size of Jupiter. So that's looking good, that's pretty promising, and this is a technique that's continuing. Now, I just have some, I guess. The other way to do it is called a transit technique. So hands up who's seen a solar eclipse. Really, you've also, there's like half of you just put your hands up there. Wow, that's amazing. All right, lucky you. Who also saw the Venus, transit of Venus? Even less. Oh, that's, okay. This is pretty cool. Like, this is the one I've seen. This is where Venus came between the sun and us, and over the course of minutes in this case, well, 20 minutes in this case, blocked a bit of the sun's light. So this is a time series. Now, in the case of a solar eclipse, the moon gets in the way and completely blocks all of that light. It's very obvious that there's an object passed between you and the sun. In the case of Venus, if you didn't have special filter glasses, you would never have been able to notice this amount of dimming. So what we're looking for are scenarios where the star and its planets happen to be in perfect alignment with the Earth, and in particular our telescopes, such that that planet passes between, that exoplanet passes between us and that distant star, blocking a tiny fraction of its light. With that technique, we can actually find just insanely, impossibly small worlds. We're finding Mercury-sized worlds around these distant stars. We're filling in all of these red points. Because we can't be sure of what blocked the light, essentially it could be a sunspot that can cause dimming, we have to wait for it to come back. We have to see that dimming occur every 10 days, then we have a star, then we have a planet with a year of 10 days. If, in this case, you've got a telescope that's only been running for a couple of years, you need to see that planet pass between you and its star several times, 3 times, 4 times, whatever. You've only been watching 2 years, that means the longest possible planetary period, that is the furthest distance away from the star, you can see is about half a year. Which means that we know that there are more distant stars out there, more distant planets out there. We just haven't had time to see them transit again. I don't think this microphone works here. So, what this means is, although there may well be planets in that black bottom right region, and indeed our theory suggests there absolutely should be, we just haven't had time to watch, to see them yet. So, that's effectively the current state of play. We now have 3,000 to 4,000 confirmed alien worlds around these distant stars. There's a lot of them, and there's a lot of weird ones. I just want to quickly draw your attention to this upper left corner. They're the mass of Jupiter, but they orbit closer to their star than Mercury does to our sun. These are insane. This is nothing we predicted. I'm a theorist, and it kills me to say this, but we didn't see this one coming. The moment it was discovered, by the way, you could explain it. Like, that was the problem. We're really good that way. You give us any data and we'll figure out why that was always the case. And never mind what we said at the last year conference. But in this case, we have these hot Jupiters. These are worlds in this beautiful graphical representation, orbiting so close to the star that they can actually be magnetically interacting with the star itself. Their whole atmospheres are being shredded. They are absolutely insane worlds, and they're really fun to try to model. If you go closer, you get these tiny Mercury-sized worlds, far, far closer to their star, and those are basically getting blasted apart. And in fact, how we've seen some of these is by essentially that. The material that's being blasted from their surface is blocking out huge amounts of the starlight. So we get a little bit of a trace of this planet, and then suddenly a whole swathe of material will get blasted off and it will block out the light. The most amazing thing, though, about this graph is that there's any planets on it at all. It is incredibly challenging to see these worlds. These techniques have been developed over the last 30, 40 years, and it's only really in the last decade that finally we're beginning to find them in any real numbers. What that means is, for us to have seen so many already, every star, on average, must have a planet. This is an incredible thought. It means that when you look up into the night sky, here's this beautiful Milky Way image, every single point of light has a planet on average around it. Now, someone asked earlier how many stars are there in our Milky Way. It's anywhere from 100 to 400 billion, depending on how you're counting. So, we'll split the difference, we'll call it 200 billion. Of those, 1 in 10 is roughly speaking a star, so 20 billion, roughly speaking a sun. So that means there's 20 billion suns, or sun-like stars out there. And thanks to the studies, we know that there must be 20 billion exoplanets around those sun-like stars. Most of which are not Earths. But what the statistics have shown us is that 1 in 5 are. In other words, there are 4 billion Earth 2.0s, Earth-sized worlds around sun-like stars. This is an incredible revelation. This has changed our view of the Milky Way. When someone asks, are we alone? What they're asking you to do is to take a bet of 4 billion to 1 against. It's pretty steep odds. Although I think the Western Bulldogs winning was still was less likely. And yet it turns out we've been pessimistic. And that's because there's a whole class of stars that we just didn't even bother considering. That is dwarf-like stars. These are tiny stars barely fusing. Stefan mentioned stars get big enough that they can ignite fusion in their core and turn hydrogen to helium and so on. These tiny dwarf-like stars will live essentially for, well, we don't actually know. We've never seen one die. In all the history of the universe today, not a single one has ever died. Our models suggest they live for trillions of years, meagerly using their resources. When we started to look, we found that there were Earth-sized worlds around those dwarf stars. And even more incredible is those worlds are at the right distance. They get enough light and heat from those tiny dwarf stars to actually have liquid water on their surface. This is the TRAPPIST-1 system. It's about 12 parsecs away, so 36 light years away. For a sense of scale, we've got our solar system at the bottom. There's Mercury, the inner world. It's in the red zone, so it's too hot. Venus is on the borderline. Earth is smack bang in the middle of the habitable zone, which is lucky, but of course is no coincidence, because that's where we are. If it wasn't, we wouldn't be here. That was obvious. And then Mars is actually just on the edge, so it's possibly a little bit too cold. All of these TRAPPIST world systems, 7 planets in total, or exoplanets in total, they all lie well within the orbit of Mercury. TRAPPIST-1 has fit an entire solar system, almost as many planets as our entire solar system, into this incredibly narrow region. But so tiny is their star that it puts out just enough heat and light to keep those closely huddled worlds warm. So there are 3 worlds. EF, do you remember? TRAPPIST-1A effectively is the star, although we rarely say that. B is the inner worlds, then C, D. E, F, G are definitely in a habitable zone. The other worlds are all potentially habitable if you have the right type of atmosphere to keep them warm and or cool. depending on your situation. But suffice to say, there are potentially 7 habitable worlds around dwarf-like stars. And what's extraordinary about these stars is that they outnumber our sun 10 to 1, perhaps even 100 to 1. In other words, that figure of 4 billion Earth 2.0s is lowballing. There are tens upon tens of billions of Earth-like worlds or at least habitable Earth-like worlds, because this would be a horrible place to live. You would have a deathly, sickly red-coloured star that's sitting in your sky. Your neighbours, your neighbouring planets, none of this like, does a planet twinkle or a star to tell, no, you just see a planet. It would just be there. You'd see its weather. It would be so close. It would be an absolutely extraordinary sight. But again, you'd probably be getting blasted from the constant eruptions from the surface of this dwarf star. So we think they're not always a great place to live. But then again, Earth, at least in the case of Earth, life has found a way in the most extreme of environments. Now, once we find these worlds, what else do we do? It's great to see them and find them. Much better is to find the life, the aliens. So we do this by looking at the spectrum of the light. We have here our sun. This is the chemical fingerprints of our sunlight. Those black regions are atoms in the atmosphere of our sun that's blocking, absorbing a bit of the light. With this, we can actually tell what it's made of. Now, we use a particularly sneaky technique, which is that when one of these exoplanets pass between us and the star, it blocks the light, and that's how we know it's there. But a little bit of the starlight shines through the atmosphere of this alien world, and then makes its way to us. In other words, we get a little chemical fingerprint imprinted on that light. We're essentially seeing its sunset and sunrise, all of them from this alien world shining through. In the same way that our Earth's atmosphere makes the light redder, so too a similar effect will happen here, and we can actually get a sense of what's going on in that Earth, in that planet or exoplanet's atmosphere. And in particular, Australia is involved in the Giant Magellan Telescope. This is coming online. It's 25 meters across. It's absolutely enormous. It's coming online in 2025. It has enough collecting area. It's big enough to collect enough light from these transiting planets to actually figure out what is the composition of the air. And in particular, what we're going to look for are things that we know from Earth that indicate the presence of life. And that is oxygen, water, and farts. Sure thing. This is Pint science after all. So we're looking for Earth, on these Earth-like worlds, water, oxygen, and methane.
That's so focusing farts.
Yeah, I did say farts. You all heard me. And that's because, at least on Earth, methane production indicates life. It can have a geological origin. But certainly, if you find methane in the presence of oxygen and water, it should break down in about 100 years. So if you see it there, you know something is replenishing it. And that something could be life. The cooler way, though, of finding life is with the Square Kilometre Array. This is not a telescope Australia is involved in. Half of it's being built here, half that's being built in South Africa. So with this, we'll be able to scan forming alien worlds, get a sense of their chemistry, but even more fun is we can potentially pick up signs of intelligent life. We can pick up mobile phone signals from Pluto. Obviously not if it's Vodafone, that goes without saying. But we can pick up alien radar landing systems for airports on distant worlds, hundreds of light years away. This isn't so crazy. There was a signal we thought we'd find. It's called the Y signal. It's gone away. We've never seen it again. But that doesn't stop some crazed, albeit visionary, astronomers looking for these alien signals. Like Professor Matthew Bales, who didn't mention this, but he's actually involved in the search for alien signals. $100 million was put down on the table by Yuri Milner, a Russian billionaire. for the breakthrough listen. And it's going to use, and it's actually using the Parkes radio telescope right now to trying to find radio signals from the closest million stars. It is the most exciting project I've ever heard of. In our lifetimes, we could answer the question, are we alone? And it's an Australian facility that's leading the way, and indeed an Australian astronomer. So that brings me to the end of the talk. And I mentioned that this is the search for Earth 2.0. But really, when you realise the incredible number of telescopes that Australia is involved in, that's leading the charge in the search for Earth 2.0, I really should have said that this is Australia's search for Earth 2.0. Thanks for listening.
Thank you for Alan and his Pint of Science and his Pint. So, any questions for Alan? Sir, can you yell loud and I'll repeat?
Given that the Earth then is relatively young as a planet, where does this leave Fermi's paradox? If there are so many life-bearing
Questions
planets.
about Fermi's paradox.
Okay, so the question was, well, Fermi's paradox, the question is, where are they? Right, if there's all of these alien worlds, and life seemingly is so easy to begin here on Earth, taking less than 1 billion years, essentially, much less actually, to get going, where are they? There's a few possibilities with this. One is that it's either really difficult, super crazy unlikely to have the chemical soup become life, and we're just lucky, right? We're the one case where that has occurred. Now, that's, like, there's no, I have no spoilers here, like, I don't know, right? It's going to be the end result of this. I'm not about to reveal that we did find aliens. Matthew? Do you want to? No, just kidding. No, he's saving that for the Nature publication. The other answer is that we've not been able to find aliens for any of our history. It is literally only in the last few decades, arguably, that we've had the technology to actually detect them. And breakthrough listen in particular is just like step. That is a game changer. But that is intelligent life. So the telescopes will find the signatures for life, which will put even more pressure. My suspicion is biosignatures will be everywhere. We'll find methane, oxygen, and a whole heap of alien models. It just means the Fermi paradox, where are they, becomes ever more pressing. And one really sad resolution to the Fermi paradox is that the moment you become technologically sophisticated, the same technology is required to send TV signals out into space and hence be detectable. Very rapidly leads on to the same technologies that will destroy you. And humans are doing a great job so far, stressing our environment and everything else. So my suspicion is the main reason is that we haven't detected anyone is simply because the galaxy is so large that by the time those signals... Ooh, I have this actually. This is the extent of humanity's radio signals. This is the Milky Way. There's a zoom in patch here. So this is the zoom in, and that blue dot is not the Earth. That is a bubble of our radio signals that we've been emitting for 100 years. So that is 200 light years across. That's all of the galaxy that would ever know that we were here and intelligent. So when you look at that, you think, oh yeah, that takes a while. The galaxy is 100,000 light years across. We would have to stay alive and communicating, transmitting into the ether for 100,000 years to guarantee that the signal is swept over. And that is just a blink of an eye in astronomical terms. So we could disappear, and then an alien civilization could arise 100,000 years later, and it's missed us. So that's probably the resolution. Space is big, and the universe is small.
But if we cease to exist, wouldn't the radio signals still keep going?
Yeah. So the question was, if we cease to exist, wouldn't the radio signals keep traveling? They would. They would travel out at the speed of light as a light echo of our civilization.
So point being, wouldn't that be the same for other worlds that have 100 billion years ago?
Yeah, but the thickness of that signal is the length of time you can communicate transmitting for. If we wipe ourselves out, if we nuke ourselves tomorrow, we have a bubble, like a thickness of radio signals 100 light years across, and it sweeps across, and once it's gone, that echo is past, and no one knows we were ever here. So it's all got very somber, actually. But yeah, I'm pretty optimistic. I do think these aliens are right there. But I definitely don't think they've come here, by the way. Please don't ask me about that. No UFOs, don't ask me.
The pyramids, come on.
Yeah, the pyramids. Sorry, can I get like some gender diversity questions? Is there any female questions or younger people in the audience who should, can you legally be here? Can you legally be here? Not drinking those shots, I can assure you that. Do you have a question though? No pressure, right? I guess. Have a think. I'll go back to you in like one question's time, okay?
What are the conditions that we classify a class of planet as habitable?
Oh my gosh, awesome. The devil is in the details. Our habitability zone is so broad as to effectively be meaningless. And I mean that in the sense that if you noticed with the green band, the Earth is right in the middle. Mars, so far as we're aware, doesn't have life in it. At least not that NASA telling us. Matthew. It's still within the habitable zone, and so too is Venus. So of the 3 worlds in our solar system that are in the habitable zone, 1 is actually got the conditions for life. So in other words, what that means is the atmosphere is everything. So it's the crudest metric. Broadly speaking, I think it's 10% of equivalent solar radiation. It's either way. But it could be almost anything. Or, yeah, some people have quite generous margins on that. And that's because the atmosphere can do a lot. So the atmosphere can actually keep you a lot warmer, right? We're having a little bit of over-cuddles from our atmosphere in that regard here on Earth at the moment. But it can also deflect a lot of heat as well. So in that way, the TRAPPIST-1 system, although there's technically 3 planets that are in the habitable zone, all 7 under the right conditions could have it. Which is why these next generation telescopes that let us actually probe the atmosphere of those worlds are the game changers. And it's incredible that it's happening in the timescale of people who are going from school into uni. They actually get to use these telescopes. They will get to find these alien worlds and tell us, old people, if they're actually inhabited potentially. No? Okay.
How could the sun form around something that's exploding and slowly expanding to the point where it will explode?
So how can the sun form around something that is exploding? Expanding, sorry.
Just talking about that graphic of yours where you picked up the planet being blown apart.
Oh, right, sorry, I see, yeah.
How do you get that planet to exist next to the sun
Oh.
which is actually being blown apart?
Oh, that is, yeah, okay, that is an incredible question. The hot Jupiters, right? The hot Jupiters, how can it be so hot and they're forming, right? Because they're getting blasted away. Exactly. So this is why, don't ever trust a theorist. We're never right, but never in doubt as well. So we didn't predict that you would get Jupiters that close because they would do exactly as you said, they would get blasted apart. The fact we saw them there was a bit awkward, so then we had to go back and think. So the current theory is that these hot Jupiters form very far away from their star, just similar to our own Jupiter, where it's cold enough, the gas, the hydrogen and helium, will stick around long enough to be, gravitationally speaking, bind into an object. But then as it's gobbling up material, it's putting on mass, and it's actually beginning to lose its speed. It's essentially moving through treacle, effectively, and it begins to spiral in. So it comes ever closer to its star, and at some point that treacle just gets blasted away, the gas gets blown away by the star, leaving it perilously close to its star, which then really begins to tear it apart. But one of the amazing things that's occurred in our understanding of our solar system is that our Jupiter has done that too. Our Jupiter formed far out with Saturn and actually came on a bit of a wander towards the inner solar system. And some models would have it as close as Mars is today, maybe even slightly closer. And then it got pulled back by Saturn, which is lucky because as it begins to swing through the inner solar system, it's kicking planets out like billiard balls. So we think there are rogue worlds that have been removed from their solar systems by these Jupiter bullies. Now, obviously this hasn't happened in the case of Earth. Maybe there is a planet out there that was once in our solar system that Jupiter kicked out. So our solar system, what we think of as this timeless clock that keeps ticking in the night sky, was actually so precise and so repetitive as to give us mathematics at some level, simple harmonic motion, all these beautiful theories. It's completely changing all the time. It's just not on our time. So over the course of millions of years, you begin to see changes. And over the course of a million years, your hot Jupiters, a lot of them will be gone. Next question? Yes.
So when you were talking about how you can see like the wobbling of like planets around stars, if you have like a multi-planetary like solar system, how do you distinguish the wobbles between different planets that are causing it?
Nice. Okay, so this is the technique is essentially very familiar to anyone who listens to music. Right? You can hear this whole cacophony of stringed instruments and different notes and different octaves all playing, but your ear can distinguish. So we can do that too. So we have the star being wobbled at different rates, and we get these over time, we get these different frequencies. This is the year of these stars. So we just have many, many different notes being played on the star. The mathematical technique to break that down is called a Fourier transform, but that's effectively a very clever way of me saying that we just listen to those different vibrations, those different modes. And actually this is the way that the gravitational waves are detected too, just on an insane scale. That little note that Matthew showed was the in-spiraling of two black holes. And we're seeing that spiral for planets. Just a super boring version of what the cool thing he showed. So basically we are listening to the different frequencies. That's as simple as that. There's nothing simple about it at all. It's amazingly difficult. And it's one of the, I think it's almost one of the I don't want to say miracles, whatever, miracles of modern science that we can do this routinely. That we find alien worlds every day. And like, we don't even report this, right? Except, and I just want to give a shout out, I think it was Mike the mechanic from Darwin. So as part of stargazing, so Brian, did Eagle see stargazing? Hands up. He saw stargazing. Okay, ABC Media has a bit of work to do. So Brian Cox came down, was at Silent Springs Observatory and Goswell Reading Side of Astronomy, and they opened up some of the data from the Kepler telescope. So this is the one that finds those transiting planets that come between us and their star. And open up that data, and Australia just went nuts and just mined it, and we're looking for patterns and looking for repeated signals. And yeah, we find a solar system which is just so bizarre. Like, it's 4 giant worlds, so super Earths in size, closer together than the TRAPPIST system. The whole thing is completely mad. And as a mechanical Darwin, I find that, and I just love it. He just basically sat up and just didn't sleep for like, 12 hours and just crunched data until he finds something amazing. And then you end up with Frank Kelly's show on Radio National, and it's just like, this is pretty cool. So in other words, you can get involved. So this is the exoplanet, exoplanetfinder.org, I want to say. Just Google exoplanet, cool citizen science Australia, and you'll get it. And get finding the world. You don't get to name them, I'm afraid. If you do have great ideas 4 names, do send them to mbells@swim.eu and he will review all your names. Choices. But I'm afraid when you buy a star name, that's not a real. Sorry. To end on a bit of a downer. We appreciate the suggestions anyway.
It's a good challenge to go out and find a star of your own. Would you please thank